Hi friends, welcome to this class. So we were discussing about stereochemistry other than carbon, right? So in this class, let us discuss the stereochemistry of sulfur compounds, right? So these are the few compounds I have written. Before going to this, let us see the basic of it. So this sulfur, it belongs to oxygen family, chalcogens, right? So oxygen family, we know that oxygen, sulfur, selenium, tellurium, polonium. So this is the thing, and sulfur is below oxygen, right? So we know that oxygen valence, if you see, it is 6, right? Can I write it like this? 1, 2, 3, 4, 5, 6, right? But oxygen, the thing with oxygen is these two lone pairs it will keep as it is, that is 4 electrons, 2 electrons, 2 electrons, total 4 electrons, it will keep it as it is. And if I have hydrogen like this, see here, hydrogen, it will be having 1 electron, here also it will be having 1 electron. 1 hydrogen means 1 electron. So it will form bond like this, sharing of bonds happens. So if you see the valency of oxygen, 1, 2, 3, 4, 5, 6. Valence is 6 only, but it will form only 2 bonds. Why it forms only 2 bonds? Because 1 bond means 2 electron, because 1 electron from hydrogen, 1 electron from oxygen, right? So 2 electron, 2 electron, 2 electron, 4 electron, 2, 2, 2, 4, 6, 8. It will be having 8 electrons. So it will follow octet rule. Right. So if you see water molecule, every time it will follow octet rule only, right? So it can't expand more than that. But with sulfur, selenium, they have the ability to expand octet. That is, from 8 electron it can form 10 electron, it can form 12 electrons, so on, right? So they can expand their valency, not valency. Valency for all it is 6 only. But they can expand the electron, that is, they can expand its octet rule. How it will form? For example, sulfur. Sulfur will also have the same 6 electron like this, right? So if I have fluorine here, so like this, fluorine will give its electron, these 2 electrons combine to form bond. So here it will form bond like this. Yeah. So it is SF2. The same SF2 can form SF4 also. Total valence of sulfur is 6, right? 1, 2, 3, 4 and 5, 6, right? It has SF, this structure also. If you see its exact structure, 4, 5, its hybridization is sp3d. sp3d means sulfur will be like this, here it will be lone pair, so will be like this, 1 fluorine here, 2 fluorine here, 3 fluorine here, and this one will be the 4th fluorine. All these will be in same plane, one will be above, 1 fluorine will be above, 1 fluorine will be below. This is the shape, not this thing. I should not write like this, because these things you have studied, right? So these all things they will ask in competitive exams, right? So see, it was having only 2 bonds, here it is having 4 bonds. And also we have seen and only 1 lone pair here, whereas here it has 2 lone pair. And we have SF6, in which all these 4 fluorines will be in one plane, and 1 fluorine will be above the plane, and 1 fluorine will be below the plane. Here no lone pairs, all are bond pairs only. So total 6 bond pairs here, 0 lone pair. Here 4 bond pairs, 1 lone pair. Here 2 bond pairs and 2 lone pairs, right? So see here, if you count the electron, it is 2, 4, 6, 8. So 8 electron here. So it is following octet rule. If you count here, 2, 4, 6, 8, 10, 12 electrons. So it has expanded its 8 electron rule, right? Because after 8, 4 more electrons it has got. Here 2, 4, 6, 8, 10 electron. So these compounds, sulfur, selenium, tellurium, polonium, these have the ability to expand their octet. They can have 10 electron, 12 electron, like that, right? So this is the thing. And one more thing. So what you understood? If I have sulfur can have bonds. It can have 2 bond, or it can have 4 bond, or it can have 6 bond. So this is the thing you have understood. So if you know the bond, then you will give the account for lone pair, because valence is 6. 2 bond means 1 electron, 2 electron, 2 electron involved. Other total 6 electrons. 6 minus 2 is nothing but 4. So 4 means 2 lone pairs, 2, 2, 4 electrons, right? That is how you can give the count for lone pairs, right? So this is the sulfur. If what happens, if see here, this same water, if I add H plus, it forms H3O plus. H3O plus. The structure of H3O plus will be like this, H. It will be having two lone pairs, right? Two lone pairs. One lone pair will be involved with this H plus. So as it gives the electron density to H plus, oxygen gets plus now, and only one lone pair will be there on oxygen, right? Initially it was having two lone pair, but one lone pair involved with the bond with H plus, so it becomes H3O plus like this. Oxygen will be having plus, and one lone pair, other are bond pairs. So it can, similarly with sulfur, it can have 2, 4, 6 bonds. If it got 3 bond, if I got a bond here, then sulfur gets positive charge. Like that you should remember, right? Because it is the lone pair is involved with it. So this is the basic we should know about valency, about bond formation, about lone pairs, these things. Once we know all those things, now let us switch to the stereochemistry of these compounds. So what are the stereochemistry? See, here on the left side of the board I have written the compounds, right? So these are the compounds. So I told sulfur, it valence is 6, right? So see, 1, 2, 3, 4, 5, 6, right? One bond means one will be shared by sulfur here like this. Total 6, 3, 4, 5, 6. Here if you see bond, 1 bond, 2 bond, 3 bond, 4 bond. 4 bond, 1 lone pair, right? So if you see total, this lone pair means this is different. A I will call this oxygen, this is B. So OET, this is C, and this is the D. So to this sulfur, all the atoms attached are different atoms. The 4 atoms attached to the sulfur are different. So this compound is optically active, right? I told for carbon 4 different atoms means the carbon becomes chiral. Similarly, if for the sulfur 4 different atoms means sulfur will be asymmetric. So it will be optically active, right? These things I have told. I should not tell again and again, but I will tell you little bit. If you didn't get, go to the first or the second video, alright, there you will get it. Similarly, see, I told sulfur can have only 2, 4, 6 bonds. If it is 2 bond, then it will be having 2 lone pair. If it is 4 bond, it will be having 1 lone pair. If it is 6 bond, it will be having 0 lone pair, right? But here if you see, sulfur is having 3 bonds, 1, 2, 3. So 3 bonds I told it will get positive charge. I can write plus here or I can write plus here. I will make a bracket here, plus here. It is understood that sulfur is having positive charge. So sulfur is having positive charge. It means there will be anion, that anion is this one, phenoxide ion, 2,4,6 trinitrophennoxide anion. So this is the thing, right? So here also you can see this sulfur is having plus charge. Instead of writing here, I will write here. So sulfur valence is 6. 1, 2, 3, lone pair 4, 5, and so it will be like 1 lone pair will be there, right? So if you see, it is this A, this methyl B, this ethyl C, and this lone pair D, right? So totally 4 different atoms. So all are different means the molecule itself is asymmetric. So that molecule will be optically active, right? So see, here I haven't made any bracket, just I have written positive charge directly on sulfur, right? So what is the molecule, man? From where did I write it? Yeah, so positive charge I have written directly on sulfur, not bracket, and anion I have written it here only, Br minus. So here also you can see this atom is different, CH2 it is. Here CH2 directly attached to circle. So this is different and this is different, and it will be having lone pair and positive charge, right? Right. So all are different. So it is the whole molecule is asymmetric. Molecule itself is asymmetric, so it will be optically active, right? So these are the things we talk about optical activity. That is, the different atoms should be attached to the central atom, that is sulfur, right? What about these things? About this also I have told you, right? I told one double bond is equivalent to a ring. It can be 6-membered ring or 5-membered ring or 3-membered ring, right? One double bond is equivalent to the ring. So here what does it mean? So it is nothing but double bond. It is like double bond. And we know that whenever we have C double bond C, if two bulky group are on opposite side, it will be E. If two bulky group are on same side, then it will be Z. So here it is like double bond, right? Cyclic ring in which S double bond O, S double bond O, both are on same side. So we can call it as Z, right? Here both are on opposite side. So we can call it as E. So these are optically inactive. These are optically inactive because they will be having any symmetry elements. Both will have plane of symmetry or anything like symmetry elements will be there. Whereas these exhibit only geometrical isomerism. Just a minute. Geometrical isomerism. Why they exhibit geometrical isomerism? I told it is like double bond, C double bond C. So they will be optically inactive and they will exhibit cis trans. So this is kind of cis, this is trans. So Z, E nomenclature they will form, that is nothing but geometrical isomerism, right? So if I want to draw the structure of this, it doesn't exist like this. It will exist like sulfur here, like this it will exist. So it is trans, right? So one double bond will be this way, other double bond will be this way, right? So if I take a plane, if I cut it, this oxygen, this sulfur will be halved, this sulfur, this oxygen will be halved, and that plane will pass like this, right? So it will be having plane of symmetry. This CH2 is mirror image of this CH2 and this CH2 is mirror image of this CH2. So it means the plane will cut this oxygen sulfur, this sulfur and oxygen into equal half. So that will be mirror image of each other, and this will be mirror image of this will be mirror image of this means CH2, right? So it will be having plane of symmetry. And I told if molecule has got any symmetry element, it can be plane of symmetry, center of symmetry, anything, that molecule will be optically inactive. So it has got plane of symmetry, and if you see neatly you will get it has got center of symmetry also. What is the center of symmetry, that I will tell you. See, so this is the molecule. So from oxygen, if you go like this, you will get this oxygen. So here I have center. So from this the sulfur is equidistant, and from here this sulfur is also equidistant. This carbon both are equidistant. This carbon both are equidistant. So this point we call it as center 2 of symmetry. From here equidistance, from here equidistance, from here equidistance, from here equidistance. So from everywhere it is equidistance. So from here also it is symmetric, here also symmetric. So such a point we call it as center of symmetry. Center of symmetry, which is indicated by I. So it has got plane of symmetry and also center of symmetry. So these molecules will be optically inactive. So they exhibit only geometrical isomerism, that is cis or trans. Cis can be written as Z, trans can be written as E, right? So this is what we have studied so many times in basic classes also, but here I have given you the exact picture of for sulfur compound, right? So this is the stereochemistry of sulfur, right? So once you understand these things, let us move on to further. So cis trans we discussed it, and I have this compound now. Right, here I have S double bond O, like this, and here I have both the side benzene ring, right? So this will exhibit cis trans isomerism. This is optically inactive, right? It will be optically inactive because some symmetry elements will be there, because of which it will exhibit geometrical isomerism. So what is this geometrical isomerism? That is nothing but cis or trans, or we can call it as Z or E isomerism, right? So how it will exhibit? If I write the structure, you will get it. So this molecule will be in both conformation. So about this conformation of cyclohexanes, I have made the video. If you go to my channel, there in playlist, you will get the conformation of cyclohexanes. There I have talked about chair conformation, board conformation. So this is what board conformation is. So in board conformation, if you see, so this is 6-membered ring, right? Totally 6-membered ring. 1, 2, 3, 4, 5, 6. So can I draw it like this? So this is the 6-membered ring in which sulfur will be here and here. Right. So see, 1, 2, 3, 4, 5, 6. So 6-membered ring. In what happens with this is this, see here I can have benzene ring, right? Benzene ring, the same exact structure. Let me draw it now. This is how we draw the board conformation, right? So this is board, and here this benzene ring is there, right? So that will be attached to this carbon like this. Here we will be having this benzene ring. So we won't show it like this. It is understood that here benzene ring is there, here benzene ring is there. Just we will do this wavy arrow like that. So this double bond O is there, right? Yes, double bond O. So that can be like this. Yes, double bond O, double bond O. Total valence of sulfur is 6. 1, 2, 3, 4. So lone pairs will be there like this, 5 and 6. So S double bond O can be like this also, or one S double bond O will be outside and one S double bond O will be inside like this, right? So these are the two structures it can have. So if both are outside, here it will be like lone pair will be here and here lone pair will be this way, right? So if this is the structure, both are outside, then we call it as cis. If one is outside, one is inside, then it is nothing but trans. So this is how it will exhibit geometrical isomerism, cis and trans isomerism, right? So and also in the book they have named it, this cis is also called as alpha form and this trans is called as beta form, right? So this is what they have done in the book, right? So I have got few more minutes. Can I cover it or not? Yeah, I have left few more concept, but let me discuss only one thing here. In next video, let me discuss the other things, right, about the reactions of these sulfurs and their conformation or the stereochemistry. That we shall see in next class. So this is the last example for this class. That is the thing, this one. So here it is again cyclohexane structure, and here we have tertiary butyl and COO, right? I have this compound, right? So this compound is cis form now. If I heat it, the equilibrium will be more towards the right side than towards left side when I heat it. So what happens, this double bond O is here, right? That will be converts to like this structure. Double bond O will be inside, right? Always this tertiary butyl we always prefer to keep it in equatorial position. This position we call it as equatorial, whereas these positions we call it as axial. We should always keep this bulky groups like tertiary butyl groups in equatorial position. About this I have told completely in conformation of cyclohexanes, which will be available in the playlist of Carter tutorials. There you can watch that, right? So this is transform. So when we heat this molecule, the percentage, if you see, if it is 25%, it will be 75% out of 100%. That is the thing. So it is like 1:4, right? Now here it will be 1:3, right? So they told at 1:4 ratio, and we heat with some boiling liquids, boiling solvents we can call like decalines, and it will be around 162 degrees Celsius. So these decalines are high boiling liquids. If we heat it like this, the cis will be converted major towards trans only, and the ratio we have told 1:4, not 1:3. Here it will be 1:3. So it is, the ratio is 1:4. 1% of cis, then it will be 4% of trans. Like that ratio it will be, right? So for some times they will ask you to write the conformation of this thing. So 6-membered ring in which NH. So you will write like this. So you will take like this. Here you will place nitrogen, right? So you have got two possibilities. Let me write both the possibilities. You can place one hydrogen here or one hydrogen here, and lone pairs will be as usual opposite here, right? So here you have placed axial position hydrogen, lone pairs in equatorial position, right? And here you have placed lone pairs in axial position and hydrogen in equatorial position. Which one is the major, or how this molecule will be there as major product? The answer is this one. This will be major and this will be minor. You will ask why, sir? The reason is, see, here we have hydrogen, here we have hydrogen. So hydrogen, hydrogen, hydrogen. So if you see, hydrogen is a small, it will occupy only small space. Whereas here we have hydrogen, no doubt. Here also I have hydrogen, but here I have lone pair. This lone pair occupies more space. So if you see the repulsion, it will be more here. Whereas here lone pairs are in equatorial position, which is away like this. So here repulsion will be less. So this will be the stable structure of this molecule. So this will be major and that will be minor, right? So sometimes what they will do, they will give this molecule. Let me give it this molecule. Now you have to tell whether which one is major. I have N, now I have replaced hydrogen by methyl, and this is again 6-membered ring. So again you will get two possibilities, in which methyl only will place it axial and lone pairs will place it here, or one more possibility, that is you will place methyl here, lone pairs here, right? Which one is major now, right? So in last class, if hydrogen was here, that was the major. If hydrogen, with respect to hydrogen I am talking, if hydrogen is at axial position, that was major. If hydrogen was at equatorial position, that was minor. Now let us talk for this molecule, the whole molecule. That is, when axial position we have methyl. So here what happens? Here hydrogen is there, here hydrogen is there. This methyl is a very bulky atom. Methyl means what? CH, H, H. So here repulsion will be very high. Because of more repulsion, this will be minor. Whereas here also repulsion is there, no doubt, it will occupy more space, but compared to methyl, it will occupy less space only. Methyl it acts like a bulky, so here more repulsion. Here this is, since this bulky atom, that is methyl, is away from this, so this will be major. So with respect to this molecule, this will be major, right? So these things you should know to write the stereochemistry. Sometimes they will give you this molecule and they will ask you to write the stable conformation of that molecule, right? So this is the thing, right? So in next class, let us see few more reactions of the sulfur compound and the stereochemistry. Till then, take care and have a great day.